Alright guys, this is chapter 5.4 and 5.5. So, in 5.4, we're going to really look at a lot of exponential and logarithmic models and exponential functions in investing. We're going to use calculator a lot, pretty much primarily in these last two chapters. So just follow along, try to follow what I do on the calculator. This steps that we've really done a lot before. We do a lot of the regression model stuff that we've already done linearly, quadratically, quartically, except now we're going to do it with exponential and logarithmic functions, so our models. So you shouldn't have too much trouble with this if you kind of got and understood how we did it before. But follow along and we'll go through it piece by piece. Example 1 says the monthly premiums for a $250,000 in term life insurance over a 10-year period increase with the age of men purchasing the insurance. The monthly premiums for non-smoking males are shown in the table below. So we have this table of values. First one, part A, says graph the data in the table with X as age and Y in dollars. B says create an exponential function that models these premiums as a function of age. So let's go about doing that right now. So if you bring up your TI, which is what I'm going to do, I'm going to have to put it split screen so that I can see all the data to type in. So we're going to use age as X and monthly premium for 10-year term insurance as Y. What you're really going to do, okay, make sure everything's cleared out. I'm going to go ahead and clear the whole calculator out. I'm going to go to Stat. So hit your Stat button, go Edit, and you're here at your list. If you have anything in your list, go ahead and clear your list out. Don't delete your list. If you do that, you can have some problems. The only way to really get a list back if it's been deleted is to reset your entire calculator. If you need to figure out how to do that, a simple YouTube search on how to reset a TI-84 calculator will give you how to do that. So I'm going to type in list 1, the age. So I'm going to go 35, 40, 45, 50, 55, 60, 65, 70, and 75. I know it's probably really hard to see how it's actually showing up in my list over here, but all you're really doing is typing these numbers in L1. I'm going to type the monthly premiums in L2. So in L2, I'm looking at 123, 148, 225, 338, 500. Let me scroll over and see the rest of them here. 783, 1,330, 2,448, and 4,400. Now, the order really does matter on here. You really want to keep these things adjacent to what they're associated with. So you want to make sure you have the 783 right next to the 60 in your list. Now I'm going to bring up the table where you could actually see it a little bit better here on the screen. So you'll notice everything lines up. You shouldn't wind up with more in one column than in the other because there's the same amount in both. You need to go through and make sure all your numbers are right. If you got all that right, to graph this, we've done this before, but just as a reminder, to graph this, I'm going to go second stat plot, and I'm going to make sure my plot 1 is turned on. Okay. I also need to make sure that it's on scatter plot. Scatter plot's the very first one with all the dots. Your X list is L1, your Y list is L2. That should all be automatic unless you've adjusted it in some other time. You can change the marks that show up if you want to, and you can change the color if you'd like, but you don't have to. Now, next thing you're going to hit is zoom. When we hit zoom, we're going to scroll down to zoom stat. By doing that, it'll show up all on your stat line. Now you notice that we must have still had something here in the y-axis or in the y1s because those lines showed up at the bottom. All that you should see is your scatter plot. So if you have a line or something that shows up, go back into your y equals and clear out whatever functions were in there. So this is our data right here. Now if we go back to the question, we've completed part A. So if we go back to the question, it says create an exponential function that models these premiums as a function of age. So we're creating an exponential function. So what we're going to do is we're going to hit the stat button. We're going to hit calculate. We are going to scroll down to exponential regression, EXPREG, and we're going to hit enter. Now your X list is L1, your Y list is L2. I'm going to do the additional step to store it. What it's going to do is it's going to store the equation into your Y. By doing that, or how to do that, you hit vars, scroll over here to Y vars, function number 1, hit enter, and Y1 is where I want it stored. So I'm going to store it in Y1. Hit enter to calculate it, and it tells me my function set up as y equals a times b raised to the x, where my a is 4.0389 ohm, and my b is 1.094611674, and it's approximated. So the a here, this 4.0389, is going to go where this a is at. This b, this 1.09, is going to go where this b is at. You're going to leave the y and the x alone. And I'll write this on the board so you can see it. But what I'm going to do first, I saved it in my Y1, so you can also see it here. If you hit graph, you can see how well it approximates your points on your graph. So that pretty much answers example 1. I'm going to write it on the board real quick so that you can make sure you understand how this works and where exactly your A goes and your B goes and how exactly to write it. But other than that, you've completed the problem. So let's write on the board real quick so we can get to example 2. I told you it was simple. You take it from the calculator. If you had to write the equation, this is literally what you'd write. I rounded to 4 decimal places. The computer might want you to, in my math lab, want you to round it to 2 decimal places, 3 decimal places, it'll let you know. But you literally write it y equals 4.0389 times 1.0946 raised to the x. And that would be your answer. Example 2. Suppose a company develops a product that is released with great expectations and extensive advertising, but sales suffer because of bad word of mouth from dissatisfied customers. Here, we've got the month, we've got the sales in thousands of dollars. It wants us to find an exponential model or an exponential function that models the data. So let's do it. We're going to go over here to the calculator. Okay, so if I pull up my calculator here, I'm going to go stat, edit, and I'm going to go to my list. I'm going to clear both of them out. So if you go up to the top, highlight L2, hit clear, and then enter, it clears the whole list out for you in one sweep. Same thing with L1, clear, enter, whole list is out. So I'm going to pull this to the right, pull this to the left so that I can see. My X is going to be month, my Y is going to be sales in thousands of dollars. So I'm going to type 1 through 8. So 1, 2, 3, 4, 5, 6, 7, and 8. And then I'm going to type my Y values in here. I've got 780. I've got 608. 475. 370. 289. 225, 176, 137, and that's it. So if we wanted to, we could graph this one as well. We can go, we don't have to really do anything. Our stat plot's already on. All we really have to do is hit zoom stat, and what it'll do is it'll regraph it for us. Now it's probably a good idea to come over here to Y and clear out this Y so that it won't mess with anything. Go back to your graph, you see it's all the same. Okay, so before our function increased on that example 1, here we've got a function that's decreasing here. So if I want to, I believe what we're doing is finding an exponential function that models this data. I'm going to hit stat. I'm going to go to calculate, and I'm going to scroll down. So we're doing exponential regression again. I'm going to store it again so we can see how well it works. So if I want to store it, I'm using the vars, y vars, function, y1. I'm going to calculate it. Okay, here's my function. So I've got y equals a times b raised to x, where my a is 999.78 and my b is 0.78. If I want to see how well that fits, I'm going to hit graph, and it fits really, really well. It almost looks like it fits perfect. If it doesn't fit perfect, it's very, very close. Okay, so the answer to part A on question number 2 would be that function that you found. Now we stored it in y1, we can look at it here, but sometimes it's kind of difficult to see because it doesn't round here. So if you needed to find it again, you could go stat calc exponential regression and find it again. It won't hurt anything. Okay, no need to store it again because it's already stored, and there it is. I'll write it up on the board real quick for you. If you wanted to write it, y equals 999.78 times 0.78 raised to the x. Here I rounded to 2 decimal places. It's that simple. Alright, so if a set of data has initial value a and a constant percent r written as a decimal, for equally spaced inputs x, the data can be modeled by the exponential function y equals a times 1 plus r raised to the x for exponential growth, and the exponential function y equals a 1 minus r raised to the x for exponential decay. So let's do a few examples given this exponential model that we've just gone over. Example 3 says suppose inflation averages 4% per year for each year from 2000 to 2010. This means that an item that costs $1 one year will be $1.04 the next year. In the second year, the $1.04 item will increase by a factor of 1.04 to 1.04 times 1.04, which equals 1.04 squared. Write an expression that gives the cost t years after 2000 of an item costing $1 in 2000. Okay, so let's do part A, then we'll come back and do part B and C. Alright, so in year 0, very first time you even look at the item, costs $1. 1 year later, it costs that $1 times 1.04. In year 2, it's going to cost at $1 times 1.04 times 1.04, or essentially just 1.04 times 1.04 like the problem said. So in year 3, you would expect it to be $1 times 1.04 times 1.04 times 1.04, right? So if we follow this pattern, in year T, it should cost $1 times 1.04 T times. We don't know what T is, but it should be T times, right? So we could just raise it to the T. And if we really wanted to simplify it, our item would wind up costing 1.04 to the T. It's that simple. Alright, so this is an exponential growth model because it's gaining 4% each time. So if what we look at is the exponential models from the equations above, what we've got is y equals a times 1 plus r raised to the either x or t, however you want to say it. So what we're looking at is our rate here is 4%. So what we got here is we've got a rate of 4%. We got to write it as a decimal. So 4% as a decimal is 0.04. And our a here is basically our initial value. Our initial value here was $1. Okay, so if we want to use the definition, what we can do is we can say, okay, that's 1 times 1 plus 0.04 to the x. So anything times 1 is just itself, so that's really 1 plus 0.04, which is 1.04 to the x. So that's your two methods. You could do it by the definition and get the equation, or you can kind of work through the logic of it and get the equation as well. So you got two options. B says write an exponential function that models the cost of an item t years from 2000 if its cost was $100 in 2000. So let's take it to the board and do that one. Alright, so if we use our equations that we know, what we've got is y equals a times 1 plus r to the x. Our rate here is still 4%, but here our initial value is $100. So using the equation from our definition, we get 100 times 1.04 raised to the x. Okay? It's that easy. Now if you want to do the other method, you could do it as well. You could use the same logic, right? So initially the item costs $100 in year 0. Alright, in year 1, the item's going to cost that $100 times 1.01. In year 2, that item's going to cost $100 times 1.01 from that first year times 1.04 from the second year. And the 1.04 is just kind of keep increasing as the years go along. So in year T, it's going to be 100 times 1.04 to the T. So whichever method works for you. If you like working through it like this and finding the answer, that's fine. If you like using the straight definition, it's pretty easy. That's fine as well. He says use the model to find the cost of an item from part B in 2010. Okay. If your initial year was 2000, we're looking at year 2010. First thing we're going to do, we're going to say, okay, 2010 minus 2000 should give us 10. So the x that we're going to use is 10. Okay. So we've still got that function from part B. We can simply do 100 times 1.04 raised to the 10. And we should get $148.02, right? 148.02. That's easy enough. So that would be your answer for part C. Your answer for part C would be $148.02. So if we're doing exponential models, we're also going to wind up doing logarithmic models. They kind of go hand in hand. Example 4 says, as table 5.14 shows, projections indicate that the percent of U.S. adults with diabetes could dramatically increase. So we have our table here. A says find a logarithmic model that fits the data in table 5.14 with x equal to 0 in 2000. Now, we've got an adjusted x here. So our year we start with here is 2010, but our x is 0 in 2000. So that means our year here for 2010 is actually just going to be a 10. Okay? For 2015, it's going to be 15. For 2020, it's going to be 20. So on and so forth. We need to take this data and we need to type in our calculator so we can find this logarithmic model. So, make sure you adjust the x accordingly. If you don't, you will get the wrong answer every time. So, x is going to go into L1. I've got 10 for the first x, 15 because we've adjusted it because x started in 2000, 20, 25, 30, 35. Let's see, we've got 40, 45, and 50. Alright. Now we're going to type in our y values. So with each y value needs to go with this concurrent x value. So 15.7, 18.9, 21.1. Typing it in is always the most tedious part. 24.2, 27.2, 29, 31.4, 32.1, and 34.3. It's always a good idea after you type these in, especially if the list is long, to go back through and make sure it looks like you've typed everything in correctly, because an incorrect data value will mess up your entire equation for your graph. So now that we have this typed in, if we wanted to, we could go zoom stat, which is number 9, and we could look at our stat plot of this. Now we've got something here in the Y. Let's get it out of the way. We can look at our stat plot here. Okay, it almost looks like a straight line, but it's got some kind of flexibility to the end of it. So let's do what the question asks. We need to go over here to stat. We need to go calc. And we need to figure out what this line is going to be if we're going to do a logarithmic regression on it. Now, it's very, very tempting to wind up going down here and using the logistic button. Whew. What we actually want to do, we want to use number 9, the natural log regression. Okay, so it's not going to be a log regression. It's going to be the natural log function with the regression. That's the one you need to choose. Okay, I'm still going to store it in my y1, so I'm going to go vars, yvars, select y1, hit calculate. It's going to calculate it for you. Essentially what you get is y equals a plus b natural log x, where a is negative 12.97 and b is 11.85. And you want to put this a here where that a is at, that b where that b is at, and that would be your function. I'll write it on the board here so that you can see it for yourself written in my handwriting. It's as simple as doing exactly what I said. Y equals negative 12.97 plus 11.85 natural log x. And that's your answer for part A. Now let's do part B and C. It says use the reported model to predict the percent of U.S. adults with diabetes in 2027. Now what we've got to ask ourselves here, we've got to remember that X is 0 in 2000. That means that in 2027 the X that we should use should be 27. Okay, so let's go over here to our calculator. Right, we've saved it in, our Y, which is really, really nice here. If we look at the graph, we can also see that it kind of models it. It's maybe not the most perfect model, but it does model it. So what I can do here, we said for year 2027, X equals 27. So what I can do is second calc value, I can type in 27. Okay, it tells me that when X equals 27, which models the year 2027, my Y equals 26.085251. So that would be your answer. Your answer will be, if you rounded it to 2 decimal places, it will be 26.09 for part B. So the percent of U.S. adults with diabetes in 2027 would be 26.09%. 26.09% here. Now C says, in what year does the model predict the percent to be 26.9 or 26.9%? Okay, so if we look at this, we need to figure out what our Y is. So you know the little trick, 26.9. Okay, if we put that in Y2 and we hit graph, I can do second calc and look at their intersection, and I can tell you what year that we're actually looking at. So I want to make sure I'm on line 1, line 2, and then they intersect. So it says they intersect at 28.92. So in approximately year 29. So that would be year 2029 approximately would be when they predict the percent to be 26.9%. Okay, so in year 2029, because we rounded up here, because this number right here was greater than 5, we rounded up to 29. We had to add that 29 to 2000 because 2000 was our initial year. It says that in part A. So the answer to part C would be 2029. Example 5 says table 5.15 contains the total percent of the labor force that is female for the selected years from 1900 projected to 2050. A says find a logarithmic function that models these data. Align the input to be the number of years after 1900. So let's go to our calculator and do this. So I'm going to double screen it. I'm going to go to my stat edit list. I'm going to clear out my old list so that I can put in my new list. Okay, so we're looking at years after 1900. That means our first year here is going to be our first year here is 1940. So because my first year is 1940, the X that I'm actually going to use is 40. Okay, so the next one would be 50. The one after that would be 60. You kind of get the point because we're adjusting for our years here. So if I come over here, I'm going to do 40, 50, 60, 70, 80, 90, 2000 would be year 100, 110, 120, 130. I've got to get back over here and scroll over to see the rest of them. Nope, that's it. So the next thing we have to type in, hit enter on that last one. Next thing we have to type in is our percent female column. That'll be 24.3, 29.6, 33.4, 38.1, 42.5, 45.2, 46.6, 47.9, 48.1, 48. Now we're trying to find this logarithmic function that models these data. So we're going to go stat, calc, and scroll down to the natural log regression. So natural log regression, just like we've been doing. Now I'm going to save it once again in my y1, so I'm going to go vars, yvars, function, y1, and I'm going to hit calculate. Okay, it tells me that my function here is y equals a plus b natural log of x, where a is negative 54.77 and b is 21.73. So my answer here to part A, see how well I can write it here with my cursor. So answer to this would be y equals negative 54.77 plus 21.73. So that will be the answer to A. Now let's look at B and what it asks. B says, graph the equation and the aligned points. Comment on how the model fits the data. Okay, so if I do zoom, stat, I should be able to see a pretty good graph of this function. Oops. Let me pull my calculator back up. Now you want to make sure the only function you have in your y's is that function. Let's clear out this y2 in here. If I graph it, it does a decent job. I mean, most of the points are really, really close. The only comment I would make is the end behavior of the graph up here doesn't seem to match what the actual data points are doing. The end behavior of this graph continues to go up, while the end behavior of our actual recorded data points seems to kind of flatten and plateau off, maybe even decreasing back down. So that would be essentially how I would answer that. That would be my comments on that data. Fits decently well, However, the end behavior on the right hand side appears not to match what our data points show. C says, assuming that the model is valid in 2024, use it to estimate the percent of women in the labor force in 2024. Okay, so if we're looking at, back to the problem, if we're looking at years after 1900, year 2024 would correspond to year 124. So here, our X that we need to use needs to be, now this isn't the answer, but the X here needs to be 124. And my screenwriting isn't the greatest. So if I come over here and I do second calc value for our X value, I type in 124. What I get is a Y value of 49.966926. Okay, I'm going to round to 2 decimal places. I'm going to say 49.97. So, use it to estimate the percent of women in the labor force in 2024. We said that that would be 49.97. So here, 49.97%. That would be your answer to part C. Hopefully this is pretty easy so far. 6 says, suppose that the retail price of an automobile is $30,000 in 2000 and that it increases at 4% per year. Write the equation of the exponential function that models the retail price of the automobile t years after 2000. Okay, so our initial year is 2000, increases at 4%, and the initial value is $30,000. We have the equation up above for this, and we have the logic to figure it out if you like that method better. I'm going to use the straight equation. So remember, the equation is y equals, the equation that we're going to use is that y equals, right up here, y equals a times 1 plus r to the x. Here we're using a t instead of an x, so I'll replace that blank. Okay, our initial value here is $30,000. So if I write the equation, it'll be y equals 30,000 times, now 1 plus 4%. 4% to a decimal is 0.04. So 1 plus 0.04 is pretty simple. So I'm just going to go ahead and write it instead of writing steps out here. So it's just going to be 1.04. And depending on the year that we are going to do, it'll be raised to the t, because it wants it t years after 2000. So your answer to A would be y equals 30,000 times 1.04 raised to the t. B says use the model to predict the retail price of an automobile in 2015. Okay, 2015, we're going to use a t of 15 because 2015 is 15 years after 2000. So now all we have to do is take our formula, go over to the calculator, and solve it out. So get back to your blank screen, $30,000 times 1.04 raised to the 15 should give you $54,028.31. So $54,028.31. So that's what our model predicts. Example 7 says, suppose that the population of a city is 190,000 in 2000 and that it grows at 3% per year. Write the equation of the exponential function that models the annual growth. Okay, we can do this. So let's look at it. Population of the city is 190,000. So y equals our initial value, which is 190,000. That's a comma. Alright, that's going to be times, it grows at 3% per year. So 1.03, and it doesn't tell us to specifically use a t, so I'm going to use that x that we're used to using. So it's all raised, or that 1.03 is raised to the x. So the equation for part A would be y equals 190,000 times 1.03 to the x. B says use the model to find the population of this city in 2010. Okay, 2010 is 10 years after 2000. So x here that we're going to use is 10. Okay, that's obviously not your answer. Your answer is going to be your y value. So we need to plug 10 in for x here. Let's go to the calculator. 190,000 times 1.03 raised to the 10. Okay, make it bigger so you can see. 190,000 times 1.03 raised to the 10. We wind up with 255,344.1121. Alright, so put this back over here. Now, we're obviously modeling the population of the city in 2010, so I can't have 0.11 of a person, so I'm just going to round it to the nearest whole number. So here, my y equals 255,000 344. A little comma right there. So your answer here for this one would be, where's my highlight at? Your answer would actually be, maybe it doesn't work. Man, I was hoping it was going to work. Anyway, your answer here is going to be your y, not your x. So be sure when you do these that you actually give the correct answer, or show that you know the correct answer to use. This is the one it will be looking for if you use MyMathLab. Example 8 says at the end of an advertising campaign, weekly sales amounted to $20,000. They then decreased by 2% each week after the end of the campaign. Write the equation for the exponential function that models the weekly sales. Now this one's different. In all the other ones we've had exponential growth because everything has increased. Here we're decreasing. They decreased by 2% each week. So because they're decreasing, we have to use that other formula, which we actually haven't yet used. So if you come back up here, back to your exponential model definition on page 2, if you're using decay or you're decreasing, you're going to use the function y equals a times 1 minus r to the x. So let's go down here to this example 8. We're going to wind up using y equals a times 1 minus r raised to the x. Okay, so it decreased by 2% each week, and our initial value was 20,000. So y equals 20,000 times, we're going to wind up doing, and I'll do the extra step here, 1 minus 0.02, because we're decreasing by 2% each week. We're going to raise that to the x. Okay. Now, we obviously need to simplify. So, 20,000. I know my handwriting is really not great when I'm trying to use a computer and a little mouse pad. Times 1 minus 0.02 is 0.98. And that 0.98 is what is raised to the x. So exponential decay is a little different, a little more difficult than exponential growth, because I see a lot of people forget to do the decay part and subtract the percent off instead of adding it. If you're decreasing or decaying, you're going to want to make sure you use the right formula. B says find these sales 5 weeks after the end of the advertising campaign. Okay, I want to find the sales 5 weeks after the end of the advertising campaign. That means we're going to use 5 for x. Okay, so if I use 5 for x, I'm going to type into my calculator. 20,000 times 0.98 raised to 5. 20,000 times 0.98 raised to the 5th power. Okay, so after 5 weeks, our sales have decreased to $18,078.42. $18,078.42. Okay, so your answer for part B would be dollars $18,078 42 cents. So you should be able to do A and B now. I don't think there's a C, but let me check real quick before we go on to example 9. There's not. On to example 9. Example 9 says total personal income in the United States in billions of dollars for selected years from 1960 and projected to 2018 is given by the following table. So we have the table here. The data can be modeled by an exponential function. Write the equation of the function, or this function, with x is the number of years after 1960. Okay, number of years after 1960. Let me get my marker out here. That means 1960 would be year 0, 1970 would be year 10, 1980 would be year 20, and so on and so forth. You got to be careful with this one because it goes by 10 increments for a while, but then it jumps to 2008 instead of 2010, and then it jumps by another 10 increment here. So don't lose track of that. Let me pull up the calculator real quick and let's type these in. So I'm going to do stat edit and type this list in. I'm going to clear my old list out first. Okay, L1, we're going to go 0, 10, 20, 30, 40, and then it's going to go to 48. And after 48, it's actually going to go to 58. So that's where you have to be real careful. You got to make sure you adjust accordingly to the year that you're actually starting at. Now we can type all the rest of it in. 411.5, 838.8, 2,307.9, 4,878.6, 8,429.7, 12,100.7, 19,129.6. And there it is. So we're going to model this with an exponential function. So make sure you have your list typed in correctly. Don't get nervous about this one when it rounds. The number that you type's actually still in there. It only has so much space to do it by. So I will tell people to be careful of that. That's fine. Don't type in 1000 or 19,030. Type in the exact number. It'll have it, but sometimes it has to round it because it only has so much space. Now let's estimate this with an exponential regression. I'm going to store it in Y1. I like to store it and be able to look at it, tell how well it does. And we're going to calculate it. So it tells us that the equation for part A, because this is where we're looking, we're going to write this as a function. The equation that we have is y equals, and our A here is 492.44. I'm going to round to 2 decimals. Our B here is 1.07 because I'm going to round to 2 decimal places there too. And that is raised to the x. Alright, so that is our answer for part A. Now, part B says, let's pull it up so we can look at it a little bit better. Part B says, if this model is accurate, what will the total U.S. personal income, or what will be the total U.S. personal income in 2015? Now, this is years since 1960. If we're talking about from 2015, so 1960 to 2015, that should give you what? About 55 years? Should give you 55 years. So the x that we're going to use for this one, remember this isn't our x answer, but the x that we're going to use for this one should be 55. Now, what we need to find is our y. So what we're actually doing is plugging this 55 in for this x. Let's go to our calculator and do this. So I'm going to clear this out. I'm going to say, okay, 492.44 times 1.07 raised to the 55. Okay, if you do that, you'll wind up with 20,345.15933. What I'll tell you about this, if you use the rounded one, sometimes you won't be close enough decimal wise for the MyStatLab or MyMathLab to give you credit. That's why if you want to find it exact, a lot of times you need to go zoom stat, especially if you have it saved correctly in your Y. You need to do that, and you need to come over here, and then you need to do second calc value x at 55. That way you get it a little more precise. So you see the answer we have here is 20,100.752, whereas the answer that we had before was quite off because we rounded. So it doesn't seem like rounding would make that big of a difference, but you're off by several hundred actually on that one. Do it one more time. Second calc value, we're using x at 55, and that's probably the answer that MyMathLab is going to want. So we'll write that one, 20,100.75. 20,100.75. Alright, now let's look at C. C says, in what year does the model predict total personal income will reach $19 trillion? Now this is one of those where you have to come over here and say, hot dang, this thing's in billions of dollars. C wants it in trillions of dollars, or $19 trillion. So I'm going to take a second to pause and go to the board. Right, we need to go from 19 trillion into billions. So let's go through this again. That's 1, that's 1,000, that's a million, that's a billion, and that's a trillion, right? So the difference between billion and trillion is right here. So that would be billion, the extra zeros is trillion. So if I want to go from trillion back to billion, so what I've got, if I've got 19 trillion, I think I got that right with the zeros, and I want to go to billion, billion, if you look at it, this is my billionths place right here. Okay, that means that 19 trillion would be the same thing as, I'll do it in a different color marker, would be the same thing as 19,000 billion. So what we need to type in our calculator and figure out is this 19,000 billion. So come over here to our calculator. 19,000 billion. Okay, so if I go y equals, I'll type in y2, 19,000. Make a graph. If I find where those two functions intersect, then I can find my answer. So we'll scroll down here to number 5, which is intersect. First line, second line, and then try to come over here and get as close as I can to where they actually intersect. Hit enter one more time. It tells me they intersect at x equals 54.1649. So at approximately year 54 is when it reaches 19 billion, or 19 trillion, 19,000 billion. So my answer here would be 54 years. But that wouldn't be my final answer. So 54 would be what my x would equal. If my x equals 54, that actually means that what I'm looking at here is I'm looking at year 2014. So the answer to part C should be 2014. So the next thing we need to look at here is this chapter 5.5, exponential functions and investing. So we kind of already looked at this compound interest function. Y equals A times 1 plus R raised to the X. Now, example 1 says to numerically and graphically view how $1,000 grows at 6% interest compounded annually, do the following. A says construct a table that gives the future value S equals 1,000 plus 1 or times 1 plus 0.06 to the T for T equals 0, 1, 2, 3, 4, and 5 years after the $1,000 is invested. So what we could do is we could do that by hand, but I'm all for doing things the simple way. So if you pull up your calculator, right, and I will write this table out on the board for you, but if you pull up your calculator, you go to y equals, clear out all this stuff that we've been doing, start from a blank one, and you type in this function 1,000 times 1 plus 0.06, close your parentheses, raise it to the X. Okay, hit the graph button. Okay, it's still going to show the points that we had before. Don't worry about those. You can turn those off if you want to go second stat plot and turn the plot off so they won't be in your function. But you don't have to do that if they don't bother you looking at them. There's the function we're looking at. Now, what we need to do is we need to figure out these values for 0 through 5. Now the easiest way to do that is hit second graph or second table, and it tells you the values for 0, all the whole numbers really, but 0 to 5 here. So instead of having to calculate each of them by hand or on the calculator by typing it in one by one, you can just go type the function in your y equals, go to your table, and it'll give them all of them for you. Let me put them on the board real quick. So here is the table. I just copied it straight from the calculator. The only difference here is that we're using an S and a T. So the X that we pull from the table is your T, the Y is your S. So value for 0 was 1,000, for 1 it was 1060, for 2 it was 1123.6, for 3 it was 1191, 4 it was 1262.5, and 5 it was 1338.2. So that should be pretty simple and straightforward. Now B says graph S equals 1000 plus or times 1 plus 0.06 to the T for the values of T given in part A. Okay, so if we want to graph it just for the values in part A, we just need to change our window. So our X min is 0, our X max is 5. If I graph that, notice it does a pretty terrible job. All it looks like is a straight line. If you want to make that look a little better, what you can do is zoom fit. And what zoom fit will do after you set a window on one of your restrictions is it'll keep that restriction, but it'll adjust the other restriction. So we still have our 0 to 5 here. If you don't believe me, you can go to your window and see it's still 0 to 5. But it adjusts your Y so that your Y kind of runs through the screen a little bit better. So you can see it's not a straight line, but it looks pretty darn close to a straight line on this window. And that's all it really wanted you to do for part B. Look at future value of an investment with annual compounding. It basically says if P dollars are invested at an interest rate R per year compounded annually, the future value S at the end of T years is S equals P times 1 plus R raised to the T. Now, the future value of investment with periodic compounding says that if P dollars are invested for T years at the annual interest rate R, where the interest is compounded K times per year, then the interest rate per period is R over K. The number of compounding periods is KT, and the future value that results is given by S equals P times 1 plus R over K raised to the KT dollars. Okay, so these formulas are very, very important. Okay, so when you're doing these problems, you got to really figure out, am I compounding annually or am I compounding periodically? And if I am compounding periodically, what exactly is that period that I'm compounding by? Now you'll see exactly what I'm talking about in the upcoming examples. Example 2 says find the future value of $10,000 placed in an account earning 8% per year for 10 years if the interest is compounded annually, daily. And then C says how much more is earned by compounding daily. Now I'm going to take this one to the board and work it out so you can kind of see it a little more clearly than me trying to scribble it here with my little notepad thing on the screen. Plus there's not as much space here for me to do. So let's take it to the board real quick. So we have our annually formula, we have our periodically formula. A says find it annually. So in our problem, P here is $10,000. So S equals $10,000 times 1 plus our rate here was 8%. So plus 0.08 raised to the T. If I simplify that, then S equals $10,000 times 1.08 raised to the T. Alright, it's just occurring to me that that might be hard to see part of the board, so I'm going to write it again right underneath it. I'm just rewriting the same thing to make sure that you can see it. I think you can, well, yeah, I think you can see that one a little better. So it's the same thing as that. I just noticed I have a kind of a glare on the board. I want you to be able to actually read it. Now daily, how is it any different? So daily will go into the periodically category. What that means is I'm going to use S equals, P here is still $10,000. Okay. Now, we're going to do 1 plus, R is my rate. My rate is still 8%. So 0.08. The only difference is I have a K here. What we're going to use for that K depends on the type of periodic that we're looking at. Here we're looking at daily. How many days are in a year? There's 365. Okay. Not talking about leap years and stuff like that. Generally speaking, there's 365 days in a year. So we're going to use 365 for our k. So we need to put it up here in the exponent too, 365, and then multiply it times a t. So this is the formula we'll use for daily. That's the formula we'll use for annually. Now, there's no really easy way to simplify this. You could type it in your calculator and simplify this piece if you really wanted to. Depending on what, I'm not going to lie, my camera died. What all I was saying is if My Math Lab wants you to type this in, they're going to tell you how they want you to round it. So what you'll do is you'll type this part in the calculator by itself to get a rounded version of it, and then stick that part in. Otherwise, they might set the form up and make you type this piece in, this piece in, and this piece in all separately based upon the form they have it written in there. If you have trouble with that, let me know. Let's go to the calculator and solve part C. C says how much more is earned by compounding daily. Okay, so what we notice here is in addition to finding the annually formula and the daily formula for part A's and B, what we really need to do is we need to find the actual value after 10 years for A and for B. So the formulas we found are important, but let's actually find these values. So going to A, we did annually was 10,000 times 1.08, and that 1.08 is raised to the 10th because it's 10 years. So the answer to A would be 21,589.25. Now if we wanted to find it for B, for daily, we'd use the formula 10,000 times 1 plus 0.08 divided by 365. Then we got to close this parentheses. We have to raise it to the 365 times 10. Okay? And what we notice is that if we compound daily, we do indeed make more, but maybe not as much more as you would actually think, right? You got 365 in the exponent, you're like, oh man, that's a really big difference between this. But at the same time, this division here kind of equals it, or evens it out some. You do make more compounding daily, but you don't make as much more as you might would think. Now the easy way to subtract these is to hit the up button, highlight that, hit enter, hit the minus button, hit up button 3 times to get you back up to this one, hit enter, and let the calculator do it all for you. So the difference, the answer for part C, the difference is $664.21. So let's get all that written in here so that you see exactly what I'm talking about. So bring my pen in here, get it all written up for you. So the numerical answer, other than your formula, for part A would be 21,589.25. And for B, we said it would be 22,253.46, with a difference. How much more is earned by compounding daily? You earn over a 10-year period $664.21. So that's your difference. Easy enough. What I've done here is taken a table straight out of your textbook, which you should have access through My Math Lab. You should have access to the online e-text. This is table 5.18. What it looks at is the continuous compounding in the number e. Basically what it does is it takes this periodic formula and it goes through and it says, okay, if I compound annually using this periodic formula and I use 1 for my t, so I do it over 1 year. And what I'm looking at is this piece right here is going to wind up equaling 2. So 1 here is because we're using 1 for r as well. So if your r is 1, which means it increases by 100%, here the number of times per year that I'm compounding is 1 because it's annually. And then it'll be t, which is 1 times that 1 that is compounding. What you wind up getting is a 2. Now if you compound quarterly, so you compound 4 times a year, then the only thing that really changes is that we get a 4 in the denominator and we get a 4 up here in the exponent. And you'll notice that this value goes up some. Now if you do it monthly, which is 12 times a year, it goes up a little bit more. If you do it daily, which is 365 times a year, then it gets to 2.71. If you do it hourly, there's 8,760 hours in a year. What we get is it gets really close to 2.7181, and you notice that it really changed much from daily to hourly. If you do it by each minute, which is 525,600 minutes in a year, it really doesn't change much from hourly either. So what you wind up getting is it basically kind of settles out. Doesn't matter, you know, how large this gets. It's like it stops. I won't say it stops increasing because it does continue to increase, but it only increases to an extent. So we've got this formula x where 1 plus 1 over x raised to the x. If we look at it, if this was a calculus class, we would look at something called the limit. But essentially all we're going to say here is as x gets very large, the future value approaches the number e. So in calculus, e is defined as the limit of 1 plus 1 over x raised to the x as x approaches infinity. Essentially, as x gets really large, it kind of heads towards this e number. And that e number, if you really wanted to see it on your calculator, all you'd have to do is type it in. You could hit second e, which is right over the divide sign. That e number is 2.7182818828, and you can see it's really not much different than that. Essentially what that says is this formula here, doesn't matter how big that x gets, it's not going to pass this number that you got on your calculator. That's where the limit kind of settles at. So if we look at the future value of an investment with continuous compounding, it's going to take that e function kind of into play. And it's going to say, okay, what I'll say is this piece right here approaches e when I compound continuously. So I'm going to replace this piece right here, sort of, with e, and I'm going to get this new equation, the PERT equation. And we've used it a few times in this class. It says if p dollars are invested for t years at an annual interest rate r compounded continuously, the future value s is given by s equals p e raised to the rt dollars. So in example 3, it says what is the future value of $2,650 invested for 8 years at 12% compounded continuously? How much interest will be earned on this investment? So let's take this to the board real quick so I can show you face to face, and we will figure out the answer on the calculator after that. Our PERT equation, s equals p e to the rt, where our future value, we don't know, that's what we're looking for, so that's our s. Our initial value here is 2,650. That's what we'll put in for our p. Our e here stays e. E is just a number. The rate that we got here is 12%. So we need to write that as a decimal, 0.12. And the time that we're looking at is 8 years. So all we really have to do is go to the calculator and type this piece in. The hardest part, and this really shouldn't be that hard, but the hardest part to these should just be figuring out what goes where and remembering your formula. Okay, so you got to remember what goes in the p, what goes in the r. Make sure you convert that r into a decimal. So it's 12%, but it needs to be 0.12 instead of just 12. You can screw up there. Make sure you type the t in correctly. Your t does have to be in years. That's something else you might want to watch for. Because if it gives you months, you'll have to convert those months to years. So let's take this, put it in our calculator, and find our answer. Gonna pull up my TI. Let's make it a little larger for you. So I'm going to type in that equation we found, 2,650 e raised to the 0.12 times 8. So I should get 6,920.995. So what I want to do, I was going to round it to 2 decimal places, but if I do that, it's going to round this 99 part up. So I'm just going to say 6,921. So 6,921. Now that's the future value. So this is actually what S is. Okay. You got to be careful with these questions. It says how much interest will be earned on this investment. So it's not looking for S. It wants to know how much interest you're going to earn. So what you really need to do is subtract this 6,921 from 2,650. Because that 2,650 isn't interest. It's your initial value. So if you come over to the calculator, minus 2,650, you should get 4,271. 4,271. So the answer for this one that you'll actually need is right here. This would probably be what my math lab would expect here. This 4,271 to answer this question directly. Before says for each of 9 years, compare using the TI-84 the future value of an investment of $1,000 at 8% compounded annually and of $1,000 at 8% compounded continuously. Okay, so for each of 9 years. So what we need to do here, first thing we need to do is come up with a formula. Okay, compounded annually, what I'm going to get is y equals, okay, the amount that I'm investing is $1,000. Okay, 8% compounded annually, 1.08 raised to the x. Alright, if I'm compounding continuously, I need to use the PERT equation. So I'm still investing that $1,000. So PE, there's your E, to the RT. So my rate is 8%, 0.08. I'm trying to make this as clear as I can. And that'll be raised to the T. So that's the two equations I'm going to type in the calculator really quick. So I'm going to pull this up, clear it out. First one is 1,000 times 1.08 raised to the x. Second one was 1,000 times E raised to the 0.08 times x. Now I'm gonna, if you hit graph, I don't think it's gonna really show up too well, and you can kind of see it on the screen we had before. If you zoom standard, it doesn't pop up at all. If you zoom, let's see, if we zoom fit, you can kind of see the red one's the compounded continuous function, the blue one is the compounded annually function. You can see there's really not much difference. Does it give a specific value? It says for each of 9 years. So let's look at years 0 to 9. So if I go to window, my x-min is 0, my x-max is 9. If I graph that, what I can see there, if you wanted to, you could do a zoom fit after that as well. See if it kind of clears up your Y a little bit better. But really what you see is they stay pretty close to the same to begin with. And then the exponential one, the PE to the RT one, does start to kind of overtake the blue one a little more significantly. If you wanted to look at the actual values, you could go second table. And from 0 to 9, let's see if I can get the whole thing on the screen. So So 0 to 9, starting at 0, they both produce 1,000. 1 year later, the annually one is up to $1,080. The compounded continuous one, really the only difference is $3.30 because it's up to $1,083.30. In year 2, you can see the difference increases a little bit more in year 3. Year 4 increases a little bit more, and that's kind of the pace that it keeps. Now in year 9, you've got 1,999. Here, you've got 2,054.4 there. So it starts to get more significant year after year, which is the same thing we saw here in the graph. But if you needed to, or if you wanted to, you could write that table down after you graphed it on the same axes. So that's really all that I wanted you to see and compare there. So you can see graphically, you can see numerically, the compounding continuously does increase it more, especially the longer you let it sit there and compound continuously. So in the short run, there's not much difference. In the long run, there's going to get to be a lot more significant of a difference. And if you wanted to, you could hit the zoom out button, and you could zoom out a while. And if you do zoom out a while, what you'll notice is it's hard to see a little bit because the zoom out function really doesn't do as great as you'd like. But if you zoom back in here, kind of notice, because your x-axis kind of, I don't know what your x-axis is at now, but your x goes from 23 essentially to 60. But you can see that there's a decent amount of separation starting to happen here, and it kind of increases the more and more you go. It's not that great depending on how you view your graph, but this one definitely is going to overtake this one the longer you stay. Example 5 says, what lump sum must be invested at 10% compounded semi-annually for the investment to grow to $15,000 in 7 years? Let's take this one to the board. Now, we want it to grow to $15,000. So $15,000 is actually our S here. Okay, we don't know the initial value. We don't know what our P is. Well, we do know it's compounded semi-annually, so it'll be 1 plus. Our rate here is at 10%. So my rate here, 0.10 over, is semi-annually. Semi-annually is twice a year. Now, we're looking at, we got to put that 2 there as well. Time period we're looking at is 7 years. So we're looking at 2 times 7, right? Now, all we really have to do at this point is solve. Okay, so we got to back solve here, figure out what P is. The good thing is we can use a calculator, right? I don't have to do this all by hand. This one's actually really not that bad. So we'll do a few steps in by hand. Let me get a marker that works a little better. Let's try this blue one. So we got 15,000. Simplify this a little bit. That's 0.1 divided. So back to it. So 0.10 divided by 2 is actually 0.05. So what I get is 1.05 here. 2 times 7 is 14. So to get P by itself, I just have to divide by 1.05 to the 14. So that P equals, that marker's trying to die on me just like my camera has been tonight, 15,000 divided by 1.05 to the 14. Well, let's take that, type it in your calculator, see what we get. Alright, so 15,000 divided by 1.05 raised to the 14 should give us $7,576.02. So if I pull this up, put this to the side so I can still see it, write it down. So what lump sum must be invested? get my pen out. Should invest $7,576.02 in order for it to grow to $15,000 in 7 years when it is compounded semi-annually. Example 6 is the last one of this lecture. It's got 3 parts. It says the data in table 5.19 gives the annual return of an investment of $1 made on March 31st, 1990 in the AIM Value Fund Class A shares. The values reflect reinvestment of all distributions and changes in net asset values, but exclude sales charges. So we've got this table here. It goes 1, 3, 5, 10, 1.23, 2.24, 3.11, and 6.82. It says use an exponential function to model these data. B says use the model to find what the fund would amount to on March 31st, 2001 if $10,000 was invested, and continued to follow this model after 2000. Is it likely that the fund will grow at this rate in 2002? So let's start with A. Come over here to the calculator. I'm going to clear everything out. Hit Stat, Edit, clear my list out. Alright, we've got 1, 3, 5, and 10. 1.23, 2.24, and 3.11, 6.82. Alrighty, now we're using an exponential function, so I'm going to do stat, calculate, exponential regression. I'm going to store this in my y. Get it a little bigger for you. I'm going to store it here in my y variable. So I'm going to store it in y1. I'm going to hit calculate. It gives me the function right here. I'm going to go ahead and write it really quick on part A. So the function I'm going to use is y equals 1. I'm going to round to 2 decimal places. 1.16 times my v value here is 1.2 raised to the x. Okay. Now, if I go over here to y, I'm going to clear out the second y one. I don't need it. That first one's the one that's stored in. I'm going to do zoom stat. When I do zoom stat, it did a terrible job. What did I do wrong? Zoom stat. Okay, I'm having some serious issues here. Let's go back to zoom standard. Alright, there's zoom standard. Now if I do zoom stat again, why is it not? The reason it's not plotting my plots is remember where I turned my stat plot off. Make sure we have it on. Then I can do zoom stat and it'll show up much better. There's your 4 points. There's your curve that estimates it. Make sure you have that stat plot on or you'll have an error just like I just had. Now, we got the answer to part A. Part B says use the model to find what the fund would amount to on March 31st, 2001 if $10,000 was invested March 31st, 1990. And the fund continued to follow the model after 2000. So 2001 is 11 years after 1990. So the X that I'm going to use, because we tailored this model, right? So the X that we're going to use, because X is years after 1990, the X we're going to use is 11. Now, that's not the answer, it's just the X we're going to use. If I bring my graph up here and I do second calc value, I type in 11, it may or may not work. It doesn't work. The reason it doesn't work is 11 is not within our screen. So we have two options. We can back our window out here and make sure that we include 11. So I'm going to back it out to 12. That's perfectly fine. Or you could do the even more simple thing, and you can go second table, and you can scroll down, because 11 is pretty close to 0 relatively. You can scroll down to an x equals 11, and it tells you that your y value here is 8.6607. So that's the value I'm going to use. I'm going to use 8.66. So 8.66. That's obviously what y equals, and that would actually be your answer for this part. So let me put it in orange or something and circle it so that you know this is the actual answer that you're looking for here. Now, C says, is it likely this fund continued to grow at this rate after 2002? Now, this example is a little older, so some of you might not even been born then, so you might not have any clue what happened after 2002. This isn't a style question I would ask you, because this isn't a history class or anything. But what did happen after 2002 was the World Trade Center was attacked, which caused a stock market tumble, and it probably wouldn't have continued to increase, actually didn't continue to increase at this rate after 2002. So major catastrophes like that can really affect financial situations. We're actually seeing it right now with the coronavirus that we're dealing with. It's got Wall Street all up in a tizzy. Everybody's losing all kinds of money in their 401ks and their other investments. So you got to watch for stuff like that. It can really affect things, and they might not continue on the same trend. They might start a new trend. But that wraps it up for Chapter 5. So now that we've actually completed Chapter 5, we get to have a quiz on Chapter 5. So I'll send an email out and we'll talk about it, and we'll probably do it next time. Other than that, if y'all have any questions, let me know, and I will try to be in touch about the quiz, and we will continue with Chapter 6 here shortly in the upcoming class periods. Y'all have a good one.